sheet title, SHM Can't Be Simpler. Fairly simple bunch of problems. So the first problem is about a particle undergoing displacement in the y direction given as a sine omega t plus b cos omega t. Like I told you in my previous class, a sine theta plus b cos theta could be clubbed together, and this is root a square plus b squared sine omega t plus phi, where tan phi is b by a, isn't it? Phi is a constant, such that tan phi is b by a. Very clearly, this motion is simple harmonic with angular frequency omega, phase constant phi, and amplitude root a square plus b squared is the amplitude of motion of this oscillator, right? Can I wipe this off? Right? Second problem is about a displacement given as y equal to 0.4 cos square pi t by 2 minus sine square pi t by 2. Now cos square a minus sine square a is cos 2a, right? So this can be written as 0.4 cos pi t, which is very clearly simple harmonic motion with angular frequency omega equal to pi, phase constant 0, amplitude 0.4, right? Number 3. The potential energy of a particle executing SHM at a distance x from the mean position is proportional to x square, obviously. So option D, that's option C. The total energy of the particle executing SHM depends on k and a, half ka squared. So for a given time constant, for a given force constant k, it depends on, it's proportional to square of the amplitude, right? And for a given amplitude, it will be proportional to, it will be linearly varying with k, right? So option Bombay. Particle executing SHM, the kinetic energy is given as k naught cos square omega t. Sorry? But m omega squared is k, right? So if you vary m, omega square will vary, but force constant is a constant, isn't it? So that will remain k, isn't it? So m omega squared is a constant equal to k. Oh, this is number 5. Oh, sorry. Okay, 5. The kinetic energy of a particle executing SHM is given as k equal to k naught cos square omega t. Now, the maximum value of kinetic energy during the motion or the maximum value of potential energy during the motion is the same and is equal to the total energy of the system, right? So the total energy of the system is k max, which is k naught, which is also equal to u max, which is also equal to u max, maximum potential energy, right? So maximum value of potential energy is k naught, which is also equal to the total energy of the oscillator. Number 6. For a particle executing SHM, the energy in rest position is u naught. That means at the amplitude position. That means u max is u naught. Rest position means what? At the amplitude position. At the amplitude position, kinetic energy is 0. The total energy is purely potential. So the total energy must be u naught, right? So u naught must be the total energy of the system. And if k is given as k naught cos square omega t, k naught is also the total energy of the system. So K naught and U naught must be the same. K naught must be equal to U naught. So option A and B. The total energy of the particle is K naught. It's also U naught. So A and B both are correct options. Yes or no? Right? Yes. Rest position where the particle is at rest, not in equilibrium. Amplitude position, isn't it? See, when a particle is executing SHM, this is the mean position, and the extreme positions are rest positions. The particle is not at rest at the mean position. It has in fact the maximum velocity at the mean position, minimum acceleration. At the extreme positions, it has maximum acceleration but minimum velocity, which is 0. Yes or no? Right? Clear? The maximum acceleration of a particle executing SHM is A naught. Where does the maximum acceleration occur? At the extreme positions. So A naught must be equal to omega squared A. A is the amplitude of motion, right? And the maximum velocity is V. V naught. Where does it occur? At the mean position. V naught. And how much is it? Omega A. Right? What is it that we need to find? The amplitude of the particle. The amplitude of the particle. What you could do is, you could square this and divide this by this. You could square this and divide this by this. So A would be V naught squared by A naught. You can find the amplitude. Right? So option A. Right? Option A. Can I wipe this off? That's problem number 7. Problem number 8. There is a block of mass m attached to a spring in its natural length. The other end A of the spring is moved with a constant velocity away from the block. Find the maximum extension in the spring. Now what you could do is convert this problem a little bit. Imagine that there is an observer moving with A with a velocity V to the right. Right? Now with respect to this observer, so if I imagine this observer to be my frame of reference, then the equivalent situation is, if I imagine the observer to be fixed, it's as if the mass m is moving to the left with the velocity v. Right? Yes or no? Right? Imagine the observer to be fixed, then in the equivalent situation, the mass m moves with the velocity v leftwards. Right? Now, so it's as if this is fixed in an equivalent situation. Right? Which means now, this kinetic energy, when it completely gets converted into elastic potential energy of the spring, that will give me the maximum compression in the spring. X max could be obtained from these considerations. Yes or no? Are you all fine with this? Yeah. Right? So these are two identical masses, m and m, and there are two springs, one of force constant K and another one of force constant 2K joined end to end. We want to find the time period of oscillation. Remember I discussed this situation in the last class. So first of all, the two K's, K and 2K, could be reduced to a single spring. These are two springs in series. So the equivalent K is how much? K1, K2 by K1 plus K2, right? So that's K into 2K divided by 3K, which is 2K by 3. That's the equivalent K. The reduced mass of the system, mu, is m1, m2 by m1 plus m2, m into m divided by m plus m. So that makes it m by 2. the omega of oscillation of each of the masses, like we discussed in the previous class, is the same and is given by root k equivalent by mu. K known, mu known, so omega known. And what's the time period then? 2 pi by omega is the time period of oscillation of each of the masses. Clear? Shall we proceed? Number 10. Two particles P and Q describe SHM of same amplitude A, same frequency F. That means omega is going to be 2 pi F, right? Omega is going to be 2 pi F. That means the same omega, same amplitude. Move along the same straight line having the same mean position, right? The maximum distance between the two particles at all times is given to be a root 2. We want to find the phase difference between the two particles. So what I could do is, let's say one of the particles, motion of one of the particles could be looked upon as a sine omega t plus phi 1. Obviously the two particles differ only in their phase constants, right? x2, the other particle, is a sine omega t plus phi 2, right? x2 minus x1 or x1 minus x2 would be the separation. These are algebraic numbers. The difference between them will give me the separation between the two particles, right? So x1 minus x2, again as you can see, is sine c minus sine d, 2 sine c minus d by 2 cos c plus d by 2. Cos omega t plus phi 1 plus phi 2 by 2, 2 cos c plus d by 2, 2 sin c minus d by 2 cos c plus d by 2. Now, what is the maximum value of this delta x? The maximum value of this delta x is like 2a sine delta phi by 2, isn't it? Because this will be different at different times. So what's the maximum value of this expression? 2a sine this is the maximum value of this expression? Yes or no? Right? Because this is varying with time. This has a maximum value plus 1, which is when delta x becomes a maximum. What is maximum value of delta x? 2a sine delta phi by 2. Delta phi is the phase difference between the two particles. Yes or no? Right? So delta x max is 2a sine delta phi by 2. Yes or no? Phi 1 minus phi 2 is delta phi, right? And that's given to be equal to, a root 2. That's given to be equal to a root 2. Or sine delta phi by 2 is 1 by root 2, right? So delta phi by 2 must be pi by 4, or delta phi must be pi by 2. Right? Fairly simple. No, they have the same mean position. It's never said that they start at the same mean position at the same instant of time. They have had the same mean position which they acquire at different instants of time. Right? Now, number 11. There is a particle which is performing SHM on a straight line, and let's say between these two positions it's performing SHM. O is the mean position, say. Okay? So A and B are 2 points where its velocities are same. Obviously that means if A is at a certain distance from O, then B must be at the same distance from O, so that at these points the particles could have the same speed, right? Now the time taken by the particle to go from A to B, where its velocities are the same, is 2 seconds. So first of all, it starts from A, it goes to B, and it does so in 2 seconds, first thing, right? After another 2 seconds, it returns to B. That means this B to Q and back to B is 2 more seconds, right? Yes or no? Now if it took to go from A to B 2 seconds, then from B to A 2 seconds. So 2 more seconds from this point, right? Now, if from B back to B via the amplitude it took 2 seconds, then from A to P and back to A, it must again be 2 seconds. Yes or no? So the time taken is 2 plus 2, 4 plus 2, 6 plus 2, 8 to come back to the same state of motion at A. Time taken to come back to the same state of motion at A is 8 seconds. So the time period of motion must be 8 seconds. Yes or no? 12 Bombay, right? Very simple. Take x is a cos omega t, x is 4a by 5, and you can proceed, right? Right. Particle, yeah, it's the same thing after. See, after all, number 12, the time taken the particle to travel a distance a by 5 starting from rest. So that means suppose this was the amplitude position and time taken to come to a by 5 from here means from the mean position 4a by 5, right? So let's say I want to find the time the particle takes to go from this point to this point. So now if a particle, let's say at t equal to 0, let's say the particle was at x equal to a, I can choose to call this instant of time t equal to 0, then the equation of motion of the particle would be given by a cos omega t, because at t equal to 0 x is a, and if you differentiate this, velocity becomes negative. That means the particle is headed leftwards, right? Now I want to find t when x becomes 4a by 5. So put x equal to 4a by 5 cos omega t, where omega is 2 pi by t, omega is 2 pi by t, and you can find t. Yes or no? See, imagine that this instant when the particle is at a is t equal to 0, right? Then the equation of motion of the particle can be described by x is a cos omega t, so that at t equal to 0 x is a, and if you differentiate this, you'll get minus a omega sin omega t. V becomes negative. Obviously at this instant of time the particle is poised to move leftwards, right? So that's why V becomes negative. Now so when the particle, this is t equal to 0, therefore now I want to find t when x is measured from O, x is not measured from the extreme position. So when x becomes 4a by 5, when x becomes 4a by 5, find t. A will get cancelled, cos, so omega t is cos inverse 4 by 5, t is 1 by omega cos inverse, where omega is 2 pi by t, etc. Yes or no? Oroni, ki bhabcho? No. No. No, 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 no. Why will it be sine inverse 1 by 5? No. Huh? No, it will not come to cos and sine inverse 1 by 5 at all. Yeah. It's not sine inverse 1 by 5. This is the answer. From the auxiliary circle, it will be sine inverse 3 by 5 if at all you consider that. Because, see, cos inverse 4 by 5 actually is the same as sine inverse 3 by 5. So, that anyways matches. But not sine inverse 1 by 5. Certainly not. So, option B is the only right answer. this angle theta varies as d theta dt is 2 radians per second. This theta is varying as 2 radians. That means if this d theta dt is omega, then omega is 2 radians per second, right? Now, P is a certain fixed point. P is a certain fixed point on the rod. And M, so P remains fixed with respect to the rod, but in terms of the xy plane, while this rod rotates as per 2 radians per second, P will occupy different positions. For every relevant position of P in the xy plane, we draw a projection of P on the x-axis, which is M. M is the projection of P. So M then is confined to move only along the x-axis. M is confined to move only along the x-axis because at all times, no matter where P lies, its projection will always be on the x-axis. So the motion of M will be along the x-axis only. But let's see what's the nature of motion, right? Now, suppose this length is L0, then this will be a variable length. Its distance from the y-axis will be variable, which is L0 sine theta, since theta is varying, right? So the x-coordinate of M will be L0 sine theta. X-coordinate of M will be L0 sine theta, where theta at any given instant of time would be 2t, isn't it? Theta would be 2t at any given instant of time, so that d theta dt is 2, right? So this is L0 sine 2t, which is simple harmonic motion with omega equal to 2 and amplitude equal to L0. So M executes simple harmonic motion with amplitude L0 and angular frequency 2. Right? So option B. Got it? So far so good, right? A particle performs SHM along a straight line when it's at a distance root 3a by 2 from the mean position. What is done is additional kinetic energy is imparted from outside, right? Other than what its original energy at P is, there is an additional energy imparted to it, which is half of m omega squared a squared. That means an energy equal to half Ka squared is added to the system, right? We want to find what the new amplitude of vibration is, A being the original amplitude. Now very clearly, no matter where the particle is, if its amplitude has been A, then its original kinetic energy must also have been half Ka squared. At this point it has kinetic plus potential. So that is its total energy no matter where it is, whether it's at x equal to root 3a by 2 or x equal to minus a or x equal to 0.7a, its total energy remains the same, kinetic plus. So its total energy at P is half Ka squared, right? Now to this energy, a similar amount of energy is added. So the new total energy at P becomes this. And will K change? The force constant will not change, right? So if K is the same force constant, and if A nu is the new amplitude, then this would be the new energy, which will be equal to the old energy plus the energy added. And this will give you A nu, which is A root 2. All's good? So there is a block of mass m equal to 2 kgs, which is executing SHM about, let's say, this position O. This is the equilibrium position, means a mean position. When the block is passing through its equilibrium position, so first of all, suppose at the mean position it has velocity v, right? And its angular frequency is omega, and a being its original amplitude, right? What is its momentum at this instant of time? 2v originally, m and 2v, right? Now, what is done is, while it passes O, an additional 1 kg mass is placed over it. An additional 1 kg mass, so that this becomes 3 kgs, right? If it becomes 3 kgs and its new velocity becomes v1, then what will not change? The linear momentum of the system. The linear momentum will remain preserved. At the equilibrium position, there are no forces acting. The spring force is also 0. So the total linear momentum will remain preserved. Okay. So what is the linear momentum initially? 2 into v. What is the final linear momentum? 3 into v1 at the mean position. At the mean position. Yes or no? Now realize that original omega, the omega here is, say, root k, the force constant of the spring, divided by the mass m, which is 2 kgs. Now the final linear momentum of the final angular frequency, this is the original angular frequency, original omega, the final omega in this state, k will not change. K will not change. Is going to be root k by the new mass 3 kgs. Yes or no? Now v at the mean position is what? Omega into a, right? So 2 times the original omega into the original a. And suppose the new a after this revision becomes a new, that must be 3 times v1, which is the new v1 at the mean position, which would be the new omega into the new amplitude. Yes or no? Omega you know, you can plug in root k by 2. A anyway is known to you. Omega 1 you can plug in as root k by 3. Root k by 3 and solve for a new, the new amplitude. Yes or no? Is that okay? So this brings us to a warm-up on SHM, an initial stint with SHM, just getting used to various basic stuff, right?